they
Right,
saturate?
We're an IQ 20 plus. Here, right, so.
Ooh.
Good news and bad news. So yeah, we're definitely going to be on the fly making adjustments here, so we should keep an eye on the data.
Oh wow.
Yeah, I'll keep an eye, and of course, Aaron and Denise will be keeping an eye. So yeah, no worries. But yeah, it's absolutely excellent conditions. It's, IQ 20, better, pretty steady the whole night, and absolutely clear. No problem.
Wow.
You picked the night.
Bueno, gente, bienvenidos a la transmisión de el Géminis junto con estos profesionales que tenemos aquí.
A very brief introduction then. How about that?
Oh, you can, yeah, I'll just do a quick view.
Yeah, yours going.
Wow.
Oh,
So we got to look forward to tonight.
absolutely.
Stunning.
It's stunning. It's stunning.
You guys were mentioning
So
Maui.
if you scroll back to the south cam, you can see a little bit of the glow right on the
yes,
edge
the volcanoes
of the
erupting.
Pluto there.
Mm-hmm.
Oh, Aaron, what is going on over there?
We
Got a lot of
had
pressure.
our latest fountaining episode yesterday evening. It stopped for now, but it's still very warm and bright.
Wow.
Stunning.
Of Kilauea volcano.
Mm-hmm.
Let's switch to DD 102 observation 124.
We have
Okay.
The goddess is trying to prevent our observations here.
No, she's always so faint. You
Nice.
Giving us some good mana here. And with that, let's go ahead and do our quick introduction to get started. I am so very excited to be here with you all for this session of Shadow the Scientist. My name is Jamika Marshall. I am the Shadow the Scientist Programs Manager and the overall session host. With me are Brian Lameau and Emily Peavy, some of our amazing Gemini staff here. And we're going to hear from them in just a moment. Also want to make sure we introduce who are actually running the telescope right now. That is Denise Hung as the telescope operator and Aaron Figueroa in the observer's chair. Now, the astronomers that we are shadowing for this session are Bryce Bolling of Eureka Scientific, Laura May Abran of Griffith Observatory, and Matthew Beliakoff of Caltech. And I'm going to go ahead and stop sharing my screen because we've already gotten started with some amazing views. So let me jump over here to Brian and Emily to get us going. Welcome, Brian. Welcome, Emily.
Okay, thank you very much, Jamika. It's a pleasure to be here. Early morning comment. All these fine people. So I'm Brian Lameau. I'm a staff scientist here at Gemini North Observatory. I am not observing this evening. I am just adjacent to our control room in Hilo, Hawaii on the Big Island. And we are observing from effectively sea level here. We have a fiber optic connection up to Mauna Kea to our telescopes. Our telescopes actually, there's nobody at the telescope this evening. We're controlling it from down here. And in fact, Denise and Aaron are the ones that are controlling it. And we are under active observations right now. So I just showed the sky on Mauna Kea just a second ago. And we're actually just setting up to take the calibration observations that will set the baseline for the comet observations coming up. So the comet observations, we're gonna turn our gigantic telescope towards the comet in about 5 or 10 minutes. And so I'll pass over to Emily, introduce herself and get us started.
Aloha, everybody. My name's Emily Peavy. I am the Senior Education and Engagement Assistant here at Gemini North Telescope. So my job is to think about the best ways for us to be communicating the science and the work that we do with our public, especially working with the people in the community of Hawaii Island. This is a very, very exciting night. This is the second time that the International Gemini Observatory has observed the Comet 3I Atlas through a Shadow the Scientist event, and our first time was very, very popular. So we were so excited in order to put together another program like this, in order to see some amazing data and information coming through. We are also happy to be answering questions through the chat. So if you're having any questions, feel free to pop them into the chat. We'll try to get to them as quickly as we can. We have quite a few people in the room here, so I might have multiple people jumping in and answering your questions. But yeah, so happy to see everyone tonight. This morning, it's 4 a.m. for us right now.
Point of context, yeah, last time we did this from Gemini South in Serapachan, but we were here in the north.
Yes.
Of course, the observers Gemini South were in Serapachan, or close to Serapachan. And that was at noon, I think, Hawaii time.
It was.
Yeah, so that was a little bit more palatable time for all of us.
It's unpalatable. But it's
we're astronomers, so.
Right.
So yeah, and yeah, I would be remiss to point out that we have the PI, the principal investigator of the program that we're observing tonight. So it's actually a rare pleasure both to have the principal investigator on and to be able to show all the information, because a lot of times we have to hide some proprietary information because because it's not necessarily shareable in the sense that there's scientific interest to protect. But here tonight we have the PI, Bryce Bolling, and so he's gonna walk us through what we're about to see. So Bryce, can I pass over to you?
Yeah, sure. Thank you, Brian. I just want to say thanks to everyone, Gemini staff and Jamaica and the Shadow Scientist Initiative to be here this morning. I know it's really, really early over there. So I just have to really appreciate your passion and support for this project. I also want to say thank you to Laura May and Matthew for being here. They're my collaborators on this project. And yeah, we are studying what is one of the original, let's say, like a pristine sample of an extrasolar system passing through our star system right now, visiting us from another star, visiting the solar system here. And we are going to be using Gemini to try to characterize and understand its composition and other physical properties. So this is some prime time science happening in real time right now. So our sequences for this morning is we're going to be starting out. We just finished some calibrations, and we're going to be doing some science observations soon. We're going to be starting out with spectroscopy using both a slit, a single long slit, and then we're going to be using an integral field unit to study the comet and its volatile contents. And then at the very end, we're going to be taking some pretty pictures. And so it'll be a little bit till then, but I'm hoping y'all will stay with us here, stay with us through the end, and to see some pretty comet spectra and pretty comet pictures coming in. Ooh, it looks like Brian is analyzing some data in real time here.
Yeah, right. So I'm just sharing the screen. So this is our active screen right now. This is what Aaron and Denise are looking at, and they're setting up on your standard observation. We'll talk a little bit later about what that actually means. But this is not the comet that we're looking at here. This is a star that we're taking observations of in preparation for observing the comet. So the comet is just now rising in the sky. This is why we're all up at 4 a.m. And so it's just starting to come up. And so as we wait for it to rise a little bit, we're calibrating our instruments just to make sure that everything looks good and that we can remove all the terrestrial effects of the observations and get to the intrinsic nature of the comet. So Laura May and Matthew, did you guys want to introduce yourself real quick?
Matthew, or hello?
Hi,
Hello,
Laura.
this is Laura May Abron. I work with Bryce. I've been super lucky to work on this object with him, and I work at Griffith Observatory. So pleasure to see you all. Hello, Jamaica, and pleasure to see you all in Hawaii and to see the volcano glow. It's very exciting, but even more exciting what we're going to see in the skies. So
That's right.
Hi, I'm sorry, I'm Matthew, graduate student at Caltech, and we've been observing this interstellar object with Bryce since basically the day it was discovered. It's been quite a journey of seeing how it's evolved and all the cool science that's happened since then. So hopefully we'll get new results right now post-perihelion. So this is very exciting.
So I'll mention we are under active observations right now. This is what Shadow the Scientist is all about.
Yes, it is.
This is not just a show. We are like actually trying to analyze the data and understand the data. The comet is very dynamic. This is our first observation from Gemini since it reappeared behind the sun. And so the brightness of the comet, what spectral features, composition of the comet, how we might take the observations has changed a little bit from the last observations that we took from Gemini South. And so myself and Bryce and certainly Aaron and Denise are going to be actively talking about the observations, and we're going to be moving things around probably in real time. So there might be crosstalk between I serve, one of my roles here is what's called contact scientist. So I support the scientists that come to our observatory to get time on our observatory. I support those observations and I help set up the technical aspects of those observations. And so I'm actually actively looking at the technical aspects right now. And part of the analysis is shown on the screen here, and I can go through what that is in a second. But it may be that we will have to change things around as things go through here. So right now we have acquired our standard star, and we are taking an integral field unit spectrograph frame of that star. So Bryce mentioned that we're going to take some pretty pictures at the end of the night. Those are pretty pictures, but they're also scientific pictures, so they're going to be taken in different colors. But that's a very coarse way of looking at an object. So Bryce, in the background, I think that's a 3-eye picture. Is that right, Bryce, in your background?
Oh, sorry. This is a comet called C2022 E3 Atlas. I can put
Okay.
a pretty picture of 3-eye.
Okay.
Yeah.
But yeah, so that would be taken in like 3 different colors, right? And so and it's made into that pretty picture there. So normally in astronomy, we either take a pretty picture or we disperse the light. So we put a prism or something, some dispersive element in front of the light and then make a rainbow. So this integral field unit observation, this is doing kind of both at the same time. So we're taking an image of this particular star, but this type of instrument allows us to get a rainbow at every single location. So it's as if we're looking at the picture behind Bryce's right ear there of the comet, but we're able to pick every little part of that comet. We're able to get a full, not just 3 color, but like 8,000 colors observation of every little part of that comet. So this provides really precise information on the source, and this will be really interesting to pick out different species that are emitting, so different chemical species that are emitting from the comet as we take the observation. So for anybody that joined us last time, at the end of the session, after we took our super pretty pictures and all gasped and were super excited, we took a spectrum. So this is the dispersion of the light to make a rainbow. And we first were like, okay, yeah, that looks like a spectrum. But then all of a sudden we changed the stretch around. We played a little bit with the image, and we saw this big plume of what turned out to be cyanide gas, and it extended out from the comet to very large scales. And so this is what we're hoping to see with these types of observations tonight: different chemical species that emit, and we pick them up in the spectrum. So Bryce is going to be using what's called a long slit spectrum. So that's going to be, I think, we just took the standard for it. So that'll be in, are we taking the IFU first? I can't remember. We are going long slit first, right? So we're going over to 3I, and so we're going to put a slit on the comet, and then we're going to disperse the light. So that's a kind of, you get one spectrum, and we'll get like a cursory view of all the chemical species there. And then we'll do spatially resolved spectroscopy with this IFU. So we'll get different species at different locations, and then we'll take an image. So that's the plan. Let's see if everything goes according to plan.
Yes, yes. Now,
it hardly ever does with astronomy.
which is the fun of it. That's the fun of it for sure. It's an adventure. Now, you did say that typically we would have all the proprietary information hidden behind the different screens that you're showing us, but this is special because right now, as Brian said, we do have the principal investigator and the colleagues with us, so they can talk us through everything that's happening, and we'll be able to see a lot more than we typically can during one of our Shadow the Scientist sessions. And so you're saying that we're doing calibration images. Is that special just for Bryce's target, or is that a regular part of the observing process before you go to each new object?
Yeah, so so just backing up a little bit. So we have 4 instruments on our telescope tonight. We have an optical imager and spectrograph, so optical light, just like what we can see. We have what's called a speckle imager, which takes really rapid pictures of the sky and allows us to get really precise spatial information on sources. We have our very high resolution infrared spectrograph called IGRINS 2, and we have our all-purpose crazy I want to do everything instrument in the near infrared GNIRS, which is the one that I'm partially in charge of. They partially put me in charge of that one. And so what we're looking at now is GMOS. So there's lots of really awesome information in the infrared, and actually Bryce and I are just setting up his other program to monitor 3I in the infrared. But tonight we're going to stay in the optical. And so this is what you're seeing right now is an optical integral field unit observation of the standard star that Bryce has picked out especially for 3I Atlas. So this particular standard star is a solar analog. Since the comet reflects solar light, you want to remove that portion of the emission, or basically normalize it out. And so anything that you see in excess is actually coming from the comet, not from just the reflection of the solar light. So that's part of the reason why you'd want to take a special observation. This is a special observation that Bryce picked for this particular target. But we do generally take photometric standards, so basically imaging standards. We normally take standards in the near infrared to take out the absorption of the atmosphere. The telescope optics are imperfect. The atmosphere is a problem from the ground. Our instruments are, despite being very awesome, are not perfect either. And so we want to not care about any of that. We want to get to the intrinsic nature of any source that we observe. And so that means, so right now, Aaron's taking a flat field. This is what's called a flat field. So you basically take a uniform illumination and you shine it at our instrument, and you see how the instrument responds.
Bueno, ahí están poniendo enlaces en los cuales, bueno, hay alguna fotografía, hay un poco de información también. Uno de los enlaces es justamente esta fotografía que estamos viendo aquí, donde vemos la cola del cometa. No es tampoco algo muy novedoso en sí, pero es una bella foto. Vamos a ir escuchando a ver qué más nos van diciendo.
In your roles, if you have time.
My name is Aaron Figueroa. I'm the observer tonight. I'm one of our science operations staff.
I'm Denise Hong. I'm also one of the science operations staff, and I'm working as the operator tonight.
So Denise is basically moving the telescope.
Tenemos la sala de control. Ahí en la parte es el primer encuadre. Ahí tenemos la sala de control del Observatorio Gemini Norte. Veremos si nos van a pasar. Veo que tienen imágenes ahí. No sé si nos van a mostrar algo directamente desde el observatorio, que es lo que supuestamente iban a hacer también, pero por ahora no lo han hecho. Así que por ahora más que nada mucha información, información espectral. Vamos a seguir escuchando a ver qué dicen.
Let me see if I can get to our. There it is. Okay, so
Thank you.
so we've actually slewed there, so we're here.
Ooh.
And so Aaron made that decision. So Aaron has the plan, and Aaron says, let's slew let's move to this target. This is we have a set of plans that are created during the day by somebody called the Q coordinator, and they make 13 or so different plans, and we match the weather, for those scientific plans. And so we are in the best variant tonight, meaning we have the most wonderful conditions possible. So we're ready to go to take some scientific observations.
Yeah.
So I'm just showing now what's called the telescope status display. This shows a bird's eye view on the left there of the telescope, and what else?
There it is.
And so there's a lot of information on here. It's pretty disorienting. But where are we? It's even hard for me to find things sometimes.
Yeah.
There it is.
So elevation. So there's a variety of different ways that you can kind of orient. Yeah, that you can orient on the sky and orient with the telescope. This one here is azimuth and elevation. So azimuth is degrees east of north, and elevation is degrees above the horizon. So we're at about 30 degrees elevation. That's not optimal. We're looking through a lot of atmosphere right now, but we're not chasing this target into the horizon. It's rising. So this will go nothing but up. And so 30 is not too bad. And we're getting incredible image quality right now, even looking 30 degrees above the horizon. So ideally you'd want to be looking straight up or close to straight up. That would give you the best image quality because you're looking through the least amount of atmosphere. But even looking way down into the muck, we're still getting really good conditions.
Absolutely incredible. And now when we were talking about it being at about 30 degrees right now, and that although it's wonderful seeing, it's not optimal. Can we talk a little bit about air mass and seeing, just to define seeing, especially for our audience? That's pretty important.
Yeah. Okay.
Ooh.
Okay.
Ooh.
We're just
No, let's talk about that.
Okay.
Oh.
So that's our acquisition image. So this isn't even like our super awesome, like pretty picture image. This is literally just, we took a quick shot of 3i Atlas. That is 3i Atlas. quick shot of it, just to get everything centered up. So Aaron is trying to find what we call the centroid of the comet right now. And this is special software that actually Aaron wrote, that we're looking at right now. And you can see what we call isophotes on the right there. Those little like weird, like kind of keyhole looking things. So that's giving lines of constant brightness in this source. So they're measuring the location of the center of this 3i Atlas, and we're going to put a slit. You can see this like kind of dark vertical area there. That's going to be a what's called a long slit. So we're just basically going to allow the light just from that part of the sky, and then we're going to throw that through a disperser, a grating, diffraction grating, and that's going to disperse out the light into a rainbow, and then it's going to be pretty quick. So before, anybody that joined us in the last session from Gemini South, I think we were waiting a good 10 minutes or so to really see the spectrum.
That's right.
That's not tonight. Tonight is 30 seconds pop off. We have a huge telescope and this thing is honking bright. So
oh yeah.
30 seconds and it's almost instant gratification by astronomy standards here. So Aaron is setting everything up. We're actually illuminating the slit on the sky. Now they just sent offsets to Denise, so we're making fine pointing adjustments of the telescope. We have this 80-ton telescope that we're trying to get to move a fraction of a fingernail on the sky, and that's what they're doing right now. So with any luck, this next image should be 3i Atlas sitting smack in the middle of that vertical illuminated line there, and then we'll put in the disperser. So right now we have a little mirror inside the instrument, and then we'll put in the disperser, and yep, so you can even see right in the center. Out there, Aaron's going to change the stretch. There you go. Okay, so a little bit off-centered in the horizontal direction, and so there'll probably be a little bit of extra movement there, and then we'll put the disperser in.
That is absolutely incredible.
So Bryce, we have a lot of people that are very interested in checking out this spectra. Have you been looking at other spectra of this comet, and what are you expecting from the spectra?
Thank you.
Yes, so this, for context, we've observed this comet before with Gemini. We observed the comet before it went through perihelion. So perihelion is the time of which the comet passes closest to the sun. So which was in late October, early November. And during that time, we could not observe the comet because it was basically in the glare of the sun. However, before the comet went to perihelion in October 29th, we observed the comet with Gemini in mid-September and late August. And so we actually have a spectrum of the comet before perihelion from late August and mid-September that we've observed, that we've already analyzed, and we've seen some really interesting cometary gas species.
Art of science.
If you would like, I could attempt to show the spectrum from our previous observations. Would y'all be interested in that?
Yeah, I think that would be lovely. I just heard Aaron say starting science, which is our way of saying we're dispersing the light, we're making a rainbow. We're making a comet rainbow.
Well, should we check the signal for the first exposure? We just want to make sure that it's kind of in our expectations.
Yeah. So Aaron's seg plot there, that'll show us pretty quickly if anything's saturated, and we can do a rough quick cut. Aaron, if you don't mind, to do a rough horizontal cut when you get the spectrum, and just get an idea of what it looks like.
Yep,
but it looks like we're getting
about what was it, about 6/7 of an arc second delivered, which corresponds to about 0.5 zenith.
Yeah, so 0.6, 0.7, since we're looking through the through the muck, it's probably not too bad, Bryce. So we're probably okay on saturation. And my guess is we'll be getting plenty of signal. So just have to keep a lookout. If you see anything red on the first observation, that's not good. So we'll just keep an eye out for red, and then otherwise, I think the signal should be good.
Well, sure. I guess I'll show what the previous observations look like. If that's all right with you, I'll share my screen real quick.
Sure. Yeah. Let's wait for the first spectrum to come out just to get a quick look, and then we can use the baseline to interpret.
And if you have it as a link, you can also share it in the chat.
That's right. Thank you, Emily.
Okay. Yeah, I'll make a quick screenshot of this.
Okay.
Thank you, Bryce.
That'll be good, since then we can be even comparing it like right next to each other.
That's right.
Without having to competing about sharing screen.
No saturation.
No saturation, and there's some definite features there.
Oh yeah, I can see the gas. Yeah, you can see these. You can see the cyanogen gas there on the far right. In the middle, you can see the C2. Yeah, so there's lots of C2. So actually, can I just kind of go ahead and share real quick? I'll just kind of show people real quick what we're looking at here.
Sure, sounds good. I will stop sharing.
Okay, so yeah, so just by hold on, I'm gonna share desktop 1. Share. Here we go. Can y'all see my screen?
Yep, perfect.
Yes.
So just by context, right here on the bottom is what y'all just saw. This is the trace, as it were. And so in the Gemini trace, it's swapped. So blue and violet's on the right, and red is on the left. But here it's kind of the opposite way around. And let's see if I can do some magic here in real time. Yeah, so this is kind of more what we just saw right here. So we saw on the far right, we saw this bloom right here. That's from the cyanogen gas. And somewhere around here in the middle, we saw another bloom like this. That's the diatomic carbon. And just for context, what we observed in mid-September before going to perihelion was this. So we saw this cyanogen gas. We saw the triatomic carbon, and then the C2. And these are what actually give the comet its green color. It's green appearance. And this is a recent image that was taken by Michael Yeager of the comet. It shows it already has this kind of bright, kind of turquoise green glow. So what we're seeing here in the spectral trace, when we see the bloom, I'm going to stop sharing screen so y'all can go back and show us the trace again. Would y'all be willing to show the trace with the audience again? That was very beautiful, actually.
On it, Bryce. Thank you.
Yep, happy to.
And in the chat right now, I'm going to drop a link to your July paper with you, Laura May, Matthew, and some of your other colleagues, so that our audience can start to see some of the insights that you've gained from your previous observations.
Okay, so this is happening so quickly compared to last time. So I brought up a separate seg plot because Aaron's monitoring the observations that are coming in. We're already on the calibration observations, Bryce. So we're going spectrum on sky, flat arc, spectrum on sky. So this is the first spectrum on sky, and so I'm getting counts that are in the neighborhood of like 250, and our prediction was around 500. So I think it's perfect. We're a little bit the seeing is a little bit worse down here than what we have in the ITC. So I think that's totally commensurate with expectations. So it looks like it's about the brightness that you predicted. So that's good.
Yes.
I think from a technical perspective, we're doing pretty good.
Oh, yes. And I see here quite well, we have the detection of cyanogen gas there on the far right of this trace plot. And that's that kind of vertical structure right there on the right. So if you go along the trace here, go towards
Here.
the right there. That's a cyanogen gas right there.
Yeah.
And if you so that looks great. That looks great in there of itself.
So just breaking it down. So this is, as Bryce mentioned, so this is a rainbow. It's a false color image. Doesn't look like a rainbow, but it is. And it's inverted relative to what Bryce showed before. So on the right is really blue. This is bluer than the human eye can see. This is like 380, 360 nanometers. So this is like ultraviolet, basically light. So that's over here on the right. And the feature that Bryce is speaking of is this one here. So we have the central portion, central rainbow of the comet. This is this horizontal line here. And anything that's extended out along this direction, it's what we would call spatially extended. So this is the outer reaches of the comet that are emitting this cyan gas. And so Bryce was also mentioning features here, and these are different species that are seen in the comet spectrum. So anything with the extended feature, and even the extent can tell you something scientifically about the composition, about the interaction with the sun. These horizontal lines that band through the entire image, these are emission from the sky. So this is actually from the atmosphere. So these are species in our atmosphere. These bands here, these are gaps in our camera. So Bryce actually set things up so that he kind of moves the rainbow around. So these gaps aren't a problem. And you can see some other structures here, these where we have dark lines that can come from various aspects of the optics. And so this is something we'll remove in the calibration process. And so I'm going to go back to our live screen. So this here is a flat. We're probably taking the next set of comet spectra now. And then we'll move over to the integral field unit observations. Right, so we're just about to take the second set of observations here, and then we'll move over to the integral field unit observations. So Bryce, do you want to kind of give us a scientific rundown of everything we're about to see and what you're going to be analyzing with these data?
Yes, so we are going to be using the spectrum to study the gas contents of the comet. So I mentioned 2 or 3 different gas species there, the cyanogen, the diatomic carbon, the triatomic carbon. This gives us some estimate of the carbon to water ratio in the comet. And it's very interesting. We want to examine that ratio and see how it compares with solar system objects. With the IFU, we're getting not just that spectral trace for one position in the comet along the slit. We're getting it over the entire surface brightness area of the comet. And so that within a very small pixel scale, for each pixel scale covering the comet, for each pixel covering the comet in that field of view with the IFU, we're getting an individual spectrum. So that spectrum we saw was just for one slice, but with the IFU, we're getting the comet spectrum over a broad area, so that we can get the spectrum of the comet.
Please see the video 2 observation 30.
We just finished with the long slit, and we're now gonna put the IFU in.
Oh, fantastic!
Yeah. So Aaron and Denise are gonna reacquire, and then we'll put the IFU in.
It says R over R max for P2.
Bryce, do you want to give us a scientific baseline? I know you have a ton of really nice slides on kind of why you would even look at a target like this. What's so interesting about this particular target relative to previous targets? What you're hoping to get out of this, the science relative to the observations that we took before?
Yeah, sure. So I can show some pictures if you would like. Is that going to interfere with setup on your end?
No, please. Yeah, I'm monitoring back here, and Aaron and Denise got it, so no worries.
Yes, we're in
Sure.
the hands of experts.
Sure thing. So here we go. I'm going to share my screen again. Let's see if I can do this in a way that doesn't cause my computer to crash. That happened before. So,
No.
yeah. It's I upgraded to the new Mac OS, which was a bad
All
idea.
right, very soon.
Can y'all see if I go up here and
Okay,
I
sweet.
share? I'm going to stop share and share a different desktop because that is showing the wrong desktop. Let's see
We were seeing your slides on that one.
Yes. So I'm going to, so it appears to show like the note taker view on my primary monitor. So I'm hooking up to my secondary monitor so that, whoa. Can y'all see my slide?
Yes, sweet.
Yep.
Yes, we can.
Yep.
Super duper. So this is this is what the other two interstellar objects look like. So we have one-eye Oumuamua and two-eye Borisov. I'm gonna see if I can go back here. See if I it only lets me go forward, it doesn't let me go back with this view. Sorry, hold on. If I go over here. Let's see. So we're very lucky to see two interstellar objects, three now. So there's three known interstellar objects: two-eye Atlas, three-eye Atlas, two-eye Borisov, and one-eye Oumuamua. And the other two objects, one-eye Oumuamua, had an inactive appearance. It was basically a dormant comet or extremely weakly active comet when it was discovered and coming through the solar system. Where two-eye Borisov, one-eye Oumuamua is right here in this top panel right here, and the bottom panel right here is showing two-eye Borisov. Two-eye Borisov was very obviously a comet. And so we had two very, very different properties. And with the discovery of the third interstellar object, that's this the new sheriff in town, three-eye Atlas, the one that we're observing tonight.
Thank you.
It also has a very comet-like appearance. And another thing,
Bryce, may you talk about how one discovers interstellar objects?
Sure thing.
Pretty large guy out there.
Yeah, let's see if I can show this. So this is the guy. This is the guy who found 3 Atlas, Larry Deneu. He is a software engineer at the University of Hawaii. He built the software that detected 3 Atlas. I'll give you a little bit of idea of what he does and how you discover interstellar objects, how you discover objects like this. So they are discovered by ground-based surveys that image the night sky multiple times. So this is a image taken, a discovery image is taken of 3A Atlas right here so it's a 4-panel plot right here. On the left-hand side, we have two exposures that are the science frame. So these are the images that come right out of the telescope. And when 3I Atlas was discovered, it was in the galactic plane. So that's why you see lots and lots of background stars. But Larry Deneu developed software that has a way to remove the stationary background stars such that moving objects, that is objects which are interstellar objects as well as near-Earth objects and main belt objects, are present in the image after the subtraction. And this is because he is taking multiple images of the comet and throughout the night. And in those multiple images, the comet is moving a little bit between the images. So in image 1, it might be at the center of the plot or the center of the image, and then in subsequent images, it moves a little bit. So with his software that removes the stars, it removes all stationary objects, but the things that remain after that removal are the moving objects. And that's what you see right here on the right-hand panel. On the left-hand panel are the science images. On the right-hand side here are the images after the stationary objects have been removed. And what remains is the comet that is moving in the sky. That's what's in this red circle right here. So Larry Deneau is a software whiz, and he created this software called Moving Object Processing System for another survey called PanSTARRS. PanSTARRS is an all-sky survey that is based on Mount Haleakala, and he used the same software for another spacecraft, for another mission called NEOWISE, which is it was decommissioned now, but it was a spacecraft that was orbiting the Earth and was designed to detect near-Earth objects. And for this third project, ATLAS, which is the Asteroid Terrestrial Last Alert System, he used that same software and applied to that in order to search for near-Earth asteroids. And there are four sites of ATLAS on the Earth right now. One is on Mauna Loa, which is across the valley from us on Mauna Kea, and one is on Mount Haleakala, which is on Maui. And two are in the southern hemisphere. One is located in South Africa, and one is located in Chile. So these four sites together provides ATLAS with a view of the northern hemisphere and the southern hemisphere, and they're onboarding, they're bringing online new sites. So there's a new site that is in the Canary Islands off the coast of West Africa that is also a new ATLAS telescope. So Larry made the software that takes those, so these surveys take images of the night sky, and they serendipitously, by accident, let's say, detect asteroids and comets. And through Larry's software, he's able to find the needle in the haystack, find the moving objects, find the moving comets, in this case, an interstellar comet, and identify them. So Larry discovered this third interstellar object on July 1st this year, but he's found numerous other objects. He's found it impacting several Earth impactors. He found a mini-moon 2024 PT5. He found a near-miss asteroid called 2024 YR4, which we observed with both of those objects we observed with Gemini. And he recently found, well, it's also another comet in news called K1, C2025 K1 Atlas, which is a fragmenting comet. So he's a very accomplished discoverer of asteroids and comets. He also used to be my landlord at one point. I rented an apartment from him when I used to work at the University of Hawaii. but that's not his, he has many accomplishments in astronomy. Sorry,
Bryce, one question. So, and I'm sure you'll get to this maybe in this slide here, but so what makes the object interstellar? So, I mean, you have like basically a 2D frame, right? You just see pictures and you just see it moving. How does one work out that it's actually interstellar rather than just something in our solar system that came from our solar system?
That's right. You get that information from the orbit. So I have a little movie here. So this is a picture of the orbital diagram, but one of my colleagues made a much better movie showing that. So this is a I'm on like picture drawing mode, and there's some kind of icon that's blocking the movie pause button here, and I don't know how to move it. Let's see. Oh, I don't want to draw on the screen. Oh, there you go. You can click. But when I click and drag and move it, it wants to go back to the place where it was. All right, so we're just gonna have to. Y'all are gonna have to bear with me here. So let's see. So this is a short movie that shows what the different orbital elements are. So when we detect a comet, we get 3 positions of the comet. We can fit an orbit to the observations, and orbits are described by a number of different parameters here. You have the sum major axis, eccentricity, and inclination, and what those are exactly is shown by this movie here. The sum major axis is the size of the orbit, how wide it is. If it's a circle, it's how wide the circle is, and eccentricity is how elliptical the circle is, or how much it departs from a circular shape.
Bueno, para los que estén del otro lado, que estén esperando nuevas imágenes del 3 y Atlas, como ven ahí yo pregunté si van a ver nuevas imágenes y contestaron que sí, que van a ver nuevas imágenes, así que solo será cuestión de seguir en la transmisión y estar atentos y esperar que compartan nuevas imágenes mientras seguimos viendo más datos científicos y más información.
Here we have the orbit, which has a eccentricity of 0.5. Now, to describe how you define an interstellar object, would Laura May or Matthew like to talk about different eccentricity values and how they define objects as being parabolic or hyperbolic or interstellar and whatnot briefly? We have a couple of assistants here. Laura May or Matthew, would one of you like to talk about that?
Go for it, Matthew.
Sure. So in our own solar system, when comets come in from the distant Oort cloud, of the Earth, but for interstellar objects, their eccentricities far exceed that value. So they're quite hyperbolic. In the case of 3I Atlas, we saw an eccentricity of 6. And there's just no way you can get that from our own solar system. That's how we know that they're coming from somewhere else in the galaxy. And crudely, though this is not exactly true, the higher the eccentricity values, it has been said, might be more correlated with them coming from farther away or a distinct dynamical age. So that need not be true. But that has been a way of trying to interpret these values.
Is there any way to?
Oh, sorry.
Is there any way to map back where the origins of these particular sources are?
Yeah, so that's a tough question, and you have to. There's so many stars in our galaxy, right? And so you kind of have to play a bit of a guessing game with the Gaia star catalog and start looking at, okay, where are the dominant sources of gravitational perturbations? Like, okay, did it encounter anything in the past million years? Because we kind of have reconstructed the local gravitational potential for that amount of time. But the farther back we start looking, of course, the larger the error bars. But I think the idea for at least 3I Atlas is that it's extraordinarily high eccentricity, and sort of the general direction that's coming at is indicating that it came from closer towards the center of the galaxy from a much older source. So the current sort of estimate is anywhere from 1 to 7 billion years of age. And I think some of the spectroscopic observations can also be used as evidence to help us understand the age. So, for example,
I was
the
going to
nickel
ask that,
to iron
Matthew.
ratio.
Which features might be helpful for age dating?
I think the nickel to iron ratio has the potential, depending on where that nickel and iron is coming from. One of the hypotheses is that the nickel, as the comet is traveling for a very long period of time in the interstellar medium, binds more effectively to carbon and oxygen, and that makes it come off the comet faster. So spectroscopic observations of 3I before perihelion were already showing that it has a lot more nickel than iron, and that could just be that on the surface, all that nickel is much more easily coming off of the comet. So it's potentially a way, there are people who argue for various interpretations of this ratio, but one potential interpretation could be that it is a tracer of the age of the comet. And we should see that in today's spectroscopic observations as well. The nickel and iron features will be there somewhere between the CN and diatomic carbon.
So I have a little slide here that shows the action of the comet in interstellar space. So one of the reasons why it's so difficult to trace back the origins of this object based on its trajectory is because the galaxy is a pretty complicated beast. So this is a plot, or a movie rather, that shows the trajectory of 3I Atlas in the galaxy. Now I've plotted the sun as a stationary point here just to kind of give a context of how far the sun is from the center of the galaxy. But in reality, the sun orbits around the galaxy just as 3I Atlas would. And one thing you might notice in this movie here, so this left-hand panel here is the top-down view. So we're staring at the galaxy from above, and we're seeing its X and Y plane. as it's orbiting around the center of the galaxy. In the right-hand panel here, we kind of see a sideways view of the trajectory of the object around the galaxy, where the bottom x-axis is the distance from the center of the galaxy, and the y-axis is how high the galaxy is above the galactic plane. And one thing I want you to notice here is that these aren't simple ellipses anymore. These aren't closed ellipses like we would see for an asteroid orbiting the sun, or an asteroid orbiting the sun is a closed ellipse. However, an asteroid or comet orbiting the center of the galaxy is not a closed ellipse. They form these spirographic patterns here. And the reason why that is because in our solar system, the gravitational potential is in the solar environment is more or less constant. However, in the galaxy, it is not constant. It is not uniform. We have things like dark matter halos. We have globular clusters, gas clouds, spirals, basically very inhomogeneous clumps of matter distributed around the center of the galaxy that can have a perturbative effect on the trajectory of the comet in interstellar space, which constantly basically makes the gravitational potential less than uniform. And this is what causes the comet to have this kind of, let's say, non-closed ellipse type shape, which makes it pretty difficult, based on the trajectory alone, to backtrace the comet where it's coming from. I'd say about 6 years ago, after the discoveries of One-Eye Atlas and Two-Eye Borisov, there was a flurry of papers which discuss potential home star systems for the interstellar comets. Matthew mentioned this with the guy that were found in the Gaia catalog. However, that information is very, it's not good enough to really pinpoint which star the comet came from due to these different dynamical effects in the galactic environment.
Thank you, Bryce. Thank you, Matthew, for that answer. I imagine it's very, very tough, and there's a lot of modeling that's involved, and there's a lot of uncertainty that's involved. I just wanted to bring us back to the observations really quickly.
Yes.
Should I stop? Let's take a look at them.
Yeah, let's take a break. Yeah,
Yes.
yeah.
Oh, and Aaron has here that the first IFU data is coming in now.
Yeah.
Perfect timing.
Wow. Let's take a look at it.
We also do have some questions in the chat that we should also make sure that take some time to get to.
Yes, please.
All right.
So I'm just showing now our screen. That's our sequence executioner. So we've just taken the first IFU observation, this 300-second exposure. And I'm going to flip over. So Aaron actually has 8 different screens that I'm flipping between. So both Denise and Aaron have 8 different screens. So I'm trying to keep oriented in all this. But the observations are here. So what we're looking at here, Aaron's now moving around in the center in the orange. That's 3-Eye Atlas. That's through the IFU. And so the IFU has little fibers in it, little lenslets and fibers. So there's a little bit of distortion there. That's what the kind of like wavy pattern that you see. That's a reconstructed image. So there's fibers at each position. In this particular case, looking at 3-Eye Atlas, and the light is piped through. And then for each one of those fibers, it's dispersed, and you see the rainbow here in the background. So that's the dispersed observation. And so each one of these elements correspond to a different spatial location. And the data are very complex, as you can imagine. And it's not obvious to me, just looking quickly at the data, where the emission of any of the species are. But once you reconstruct this image, is this the 73? Is there an IFU reconstruction of the spectral observation, Aaron? This is 272?
272 was the acquisition
Through
image.
if you, yeah. Do you have a reconstruction? Does SegPlot do the reconstruction for
SegPlot
GMOS
does
IFU?
not do GMOS IFU reconstruction.
No.
I might do it.
So if you're looking at gene ears, you definitely have that feature. So yeah, so if we had the ability to reconstruct, we might see different parts of the comet, especially if we could step through in wavelengths. So if we were stepping through to different wavelengths, we could see the comet start to like different spatial regions of the comet. They would start glowing differently. So that would be really cool.
Would be awesome.
Unfortunately,
do we
don't
have an
that.
estimate of the signal? I mean, it looks beautiful. You can definitely see the comet right there. You can see the tail, it looks like.
Yeah. So it's 273. You bring it up interactively. Yeah, so we're getting like 100 to 200 counts peak. So about 150. That's basically right what we were thinking. So we're doing great.
I'd say this has been a success. It's quite successful.
Yeah. So it looks great. So now comes the hard work. Bryce will have to take all of the flat field frames that we took before, something called an arc frame, which allows us to. So I promise this is a rainbow. This is a false color image. We deal with numbers when we take these images, so we need to map locations in the x direction, the horizontal direction, into wavelengths. So we need to say that particular location on the image is this wavelength, and then one can then try to identify various species that are in the cometary spectra. So you know the wavelength of CN emission or C2 emission on Earth. There is a little bit of a shift when you look at an astronomical object in our solar system. So it's moving very fast. It's moving 150,000 miles an hour, something like that, like 300,000 kilometers per hour. So this induces a little bit of a shift to the wavelength of the emission, but you can remove that effect. That's called the Doppler effect. You can remove that effect and then find the corresponding wavelength of the emission of different species. And so that's and then taking the standard star observation and normalizing that out. So all that has to be done post this observation to make these really amazing science analysis ready data, which Bryce and his team can then look at and try to pick out different species. So it's a little bit difficult to pick out what's happening here, but the banded features of light, that comes from the comet itself. The gaps, horizontal gaps here, where we see dark, that's sky. So we actually have fibers that are pointed, a separate bundle of fibers that are pointed towards the sky, and that's removing the sky background. That's allowing us to estimate the sky background at the same time, simultaneously with taking the comet observations. I don't know, Bryce, if there's anything else you want to mention.
No, that was beautiful, Brian. And I'm just gonna ask, where are we right now on the sequence? Are we finished? Do we have more IFU exposures to go? Or
Yep. So we're actively taking the second 300-second one at the 540 central wavelength. We'll then go to flats and arcs, and then we'll finish that up with another 2 times 300 seconds at a different central wavelength, and then that'll be it for the spectral observation. Man, already, wow, this is moving fast. So that'll be it for the spectral observations, and then we'll go to the pretty pictures.
Oh, pretty. Yes, yes.
So our plan is to take 4 different bands, so 4 different colors. So we'll do like kind of a green a band, so green color, a red color, a kind of red, near infrared, as far as human eyes can see, and then further red than the human eyes can see. So those will be the 4 colors that we'll take the observations in.
Yes. So Matthew's been and Laura May have been answering questions there in the chat. Please keep those coming. And let me get to one that came in earlier today when we first got started. From Vonnie, what has been the most intriguing part of analyzing and observing 3I Atlas? And that's to everyone here, because I know with Bryce, Laura May, and Matthew, with Shadow of the Scientist, we had our first session with 3I with Bryce and Matthew and Laura May using Keck, maybe a week or 2 after 3I was first discovered by Atlas. So yes, we'd love to have your insights, Bryce, Matthew, Laura May.
Laura May, would you like to discuss that a little bit, or are you wanting to take a break? I think Laura May might be taking a break right now. But what I will say is that whenever these things are discovered, these interstellar objects, they're somewhat startling. When the first interstellar object was discovered, Oumuamua, I thought it was a joke or maybe a glitch of some sort. And I actually was not really interested in doing observations or taking observations of it. But when it starts to become like a real, okay, yeah, this is real. This is a real thing. Then you realize, like, wow, okay, we are actually seeing a piece of a macroscopic piece of another star system, and there's this opportunity to study it in person. So there's this kind of dream of let's say scientists. They want to study the composition of extrasolar systems. They want to study things like exoplanets and debris disk and protoplanetary disks, but it's very difficult to do that from the solar system, from our perspective on Earth. They're so far away in the galaxy, and there's we're limited on the amount of information, so the type of objects we can detect, and the kind of inference we can make on that. For objects that we're now getting the capability of direct detecting planets, young planets that are hot, just recently formed, and getting spectra of planets either from direct imaging or from transmission spectroscopy when the atmosphere of the planet is seen through a star as the exoplanet is transiting. We're looking at dust, like micron, like very, very fine grained dust around other stars that are detected in the infrared, visible light, as well as longer wavelengths.
So Bryce, I'll just mention that actually, so we haven't really touched on this too much, but Gemini is a Q observatory. We've cordoned off this time tonight, especially for the 3I Atlas observations. But we had a whole slew of observations that came earlier in the night. I think one of our first observations were of really distant galaxies. So this is one of the really awesome parts of Gemini observing, is you kind of just go all over the universe all at once. And so we started the night with really distant galaxies, so about 1.5 billion years after the Big Bang, so when the universe was about 10% of its current age. And we now have gone all the way to the solar system. But what we did in between, if I read the night log correctly, is we did a transit observation. So one of the instruments that I mentioned earlier, IGRINS 2, is a high resolution near infrared spectrograph, and we did exactly what you just mentioned. So there was a planet that went in front of its host star, and by looking at the ingress, the occultation, and the egress, the scientists there are hoping to pick out some features of the planetary atmosphere. So it's really amazing that we kind of did all of these things all in one night. And the science talks to one another. Like, I don't do solar system science. I do stuff that's very, very far away. But I mean, the methodology is very similar. The scientific questions are very similar, and they interlink with one another. And so there's a lot of synergy here that we utilize at Gemini.
Yeah, and to also talk about how amazing Gemini is. When I first got to the base facility, walked into the control room, they were observing a supernova rim that I
Oh, right. Okay.
Yes,
So, yeah.
yes, right.
So an exploded star.
It was absolutely incredible. So that really highlights the extreme capabilities that Gemini has. Yes.
Yeah. So we went from like some of the first galaxies ever to the planetary atmosphere of a planet outside of our solar system, to the remnant of exploded star, to an interstellar visitor into our solar system. I mean, you can't really ask for more than that.
Right. All in a good evening's work. Incredible. Yes, thank you, Nikki. Absolutely. And so we definitely have questions in the chat. Let me go back here. So a question here from Ivan. How long does the comet need to cross over its galactic orbit one time? Ooh.
So the galactic orbital period of 3i Atlas is about 250 million years. So that means the amount of time it takes to go around the galaxy once. And so it's likely not it's not its first rodeo. I would say it's probably been around the galaxy quite a bit.
Otherwise known as instantaneously in astrophysics, right, Bryce?
Oh, right.
In extragalactic astrophysics, we say 100 million years is 10 to 100 million years is instantaneous, just to give a cosmic scale.
Oh, okay. And we have another question. Sorry. And this is actually, let me just get here. This question is, I have a question about the rate of occurrence of interstellar comets. Should I type out the question? Yes, ask your question via audio. Yes. And so this is actually a question from the Shadow of the Scientist founder and faculty director, Raja Guhathakurta. Let me quickly make Raja a co-host here, and then Raja, yes, we'd love to hear your question.
And so just for context, what I'm showing right now is more calibration observations. So we're actually not pointed at the comet right now. We're pointed at our internal calibration environment. This is an arc frame. So this is actually an elemental lamp that's being lit up. And all these vertical lines are different elemental species of known origin that we can use to calibrate the observations. So this is taken near simultaneously, sequentially, with the 3i Atlas observations to allow Bryce and his team to calibrate it out.
And we did just get a notification in the chat from Aaron that we'll be finishing the IFU observations in about 15 minutes. And that was a question from William Chin. Thank you, Aaron, for answering that. Okay, so Raja, your question.
Thanks, Jamika, for making me co-host. So my question is about, this is the third interstellar comet known, and it's been about 5 years since the first one came through, and so that's one every couple of years with the current technology. What is thought to be the rate of interstellar comets coming through the solar system? Surely there are ones that are, it's a multi-part question. Surely there are ones that are too small to be detected by current technology. So perhaps the answer right now we have is based on the big ones that have come through. And is there a sort of model that predicts how often these things should come through the solar system? So, and I'm sorry, this is such a rambly question.
Oh,
thank you, Raja.
No, that's a great question, Raja, and one that we're intensely interested in. So it's thought that each star system, which forms planetesimals, ejects about 1 trillion objects, like interstellar object size, into interstellar space from its star system. So this is we have a lot of we think that there are a lot of interstellar objects floating around the galaxy. As for the frequency of which those which pass through our solar system, it's thought that for about 100 meter, 200 meter to maybe a kilometer-ish size object, there are about 0.1 objects per cubic astronomical unit. So this would imply that within the orbit of the Earth, that is in the distance from the Earth to the Sun. Sorry, when I said it's not cubic AU, it's within 1 AU distance from the Sun. So there's 0.1 objects, ISO objects within 1 AU from the Sun. So it's within the distance, within this distance, it's thought that there's about 0.1 of these interstellar objects.
Thank you for that, Bryce. Another question from Rob. Although it's not possible to ascertain from what star an interstellar object came from, can we get the right ascension and declination of the projection of the tails of the orbital hyperbole?
Yes, sure. So 3i Atlas was coming from an RA of about 19 hours minus 19 degrees. It was found in the southern hemisphere. You can observe minus 19 degrees declination from Hawaii. That's certainly doable. But you have a benefit, or let's say, if you are in the southern hemisphere for observing something at that minus 19 declination. And on its way out, it will be going, I believe, Matthew, do you know this? I think it's like something, it's going in the positive declination direction. Because this is a retrograde object. So it was coming in from retrograde orientation. I think it was like minus 170 degrees inclination. So it's coming from below, and it's so it should be going from southern declination to northern declination on its way out. Matthew, do you know the exact R?
I don't remember the exact RA deck. I know that I think the final inclination is going to be around 5-6 degrees or so. So it does change
above the orbital, above the ecliptic, right? So it's like minus. So it'd be 175 degrees inclination. So five degrees above the orbital.
Yeah.
So Bryce, I just want to let you know, since we have such wonderful conditions tonight, I'm dropping the exposure time a bit of the direct images that are going to come up here shortly in about 15 minutes. So I dropped them down to about 2/3 of the previous exposure. This should keep us from saturating, but we'll have to keep a close lookout for it. So I'm just going to check in with the control room, see what. Actually, Aaron, what are you reading off of P2 right now?
In terms of guide counts?
No, in terms of.
Oh, you want seeing?
Seeing, yeah.
Yeah, seeing is, we'll estimate a good, decent, actually real good IQ 70.
Okay, all right. So yeah, that should be, we should be safe then. One in the I band, we're at 1 second, so that's our minimum. So we don't have a whole lot of play there, but we have some play in the other bands. So we'll take a look out. I mean, it's gonna be rapid sequence. So if if we slightly saturate, then we can always go back and pop it off again. We should have enough time.
So I just want to say that these images have they're not just pretty, they're not just for our science, for the Gemini related science. They actually have a practical purpose. Matthew is leading a program to study 3A Atlas with the James Webb Space Telescope. And we just had this discussion in the last 12 hours, needing these images from Gemini for a specific purpose. Matthew, do you want to talk a little bit about that, as well as your the science and your program with James Webb?
Yeah, thank you. So, yeah, Bryce and I are collaborating on this project to look at 3i in the mid-infrared, which is perhaps the best wavelength range of all because you get really everything in there. You get both organic features and you have silicates, so you can actually get the composition, not just the amount, but the composition of the dust. So you know if it's magnesium rich or if iron rich. We're going to be using a similar sort of eye of view to the one you're seeing on the bottom left of the screen, but mounted on James Webb. And the trouble is the field of view, the angular sort of size on the sky that you can see is quite small, and you have to have very precise tracking. So we need to know where 3i is, right? Very exactly. And so we know where it is today. You know, we'll look at it, we'll get its position. And the trouble is, okay, where is it going to be in a month, right? This is a comet. It has non-gravitational acceleration, right? The gas is coming off, which is giving it a kick in one direction or another. And so we really need to characterize these really well for our James Webb observations to succeed. We need precision of something on the order of around 1 arc second. I actually don't know what the field of view is on this eye view here. But yeah, we need to be very, very precise for our observations to succeed. James Webb has the additional issue of can only track so fast, right? From the ground, our telescopes can be quite quick and don't have these issues. With James Webb, we need to conserve its fuel, not encounter any, other issues with turning the telescope too fast. And so we have to split our observations into these little chunks and try to just grab these quick snippets of 3i as fast as we can. But yeah, we'll have those observations around December 10th to 14th. And so hopefully all of this data will build up a good picture of 3i Atlas. And 3i, I think, will be probably the best interstellar object for quite a long time. It is quite large, passing very near, and we'll be discovering many more. But I think 3i is a very unique opportunity.
Yes, and
Absolutely.
so Matthew mentioned this a little bit, is that our images that we're going to be taking from Gemini are going to be used to help those James Webb observations, because we are going to be measuring very well, thanks to the great seeing in conditions of Mauna Kea, the position, we call it the astrometry of 3i Atlas. And we're going to be using that to inform how to point the James Webb Space Telescope and image the comet using its instruments.
Congratulations, Matthew. That's so very exciting to you and Bryce, of course. And I'll definitely be following up with you to find out what you're learning from your observations there with the James Webb Space Telescope. And we have a kind of a comment here about that. Is the comet too bright at the moment for JWST to look at, Matthew?
No, if anything, we want it to be brighter, right? In the mid-infrared, these are always tough observations, which is why, first of all, from the ground, the atmosphere blocks out most of that wavelength range. And just in general, it's been tough, right? There are not very many observations that have been done in the mid-infrared of solar system objects, period. A lot of the times, because you have to be quite close to the sun, you need to be very hot so that your black body temperature is high enough. You're getting a lot of flux coming off of the comets. And so 3i in December is going to be sort of at the perfect time to do this. And, this is how we got the idea of doing this proposal. Bryce, came to me and was like, oh, this is, super bright. Maybe we can do it in the mid-infrared. I quickly did some math and turns out, yeah, fantastic. We can do this one in the mid-infrared. For Borisov, we wouldn't have been able to do very good observations with James Webb, at least in the mid-infrared. In the near-infrared, possible, but past 5 microns, not really.
Yeah, so I'll say one of the reasons why Matthew got the time for the James Webb observations is because of the uniqueness of this opportunity. There's actually already a James Webb Space Telescope program to study 3i Atlas. However, their instrument configurations that were approved by a review committee and so on assumed a very faint object, assumed sort of a kind of a worst case scenario. However, 3i Atlas is kind of a black swan, let's say, defied our expectations of how bright an interstellar object could be, which enabled some unique science opportunities in Matthew's proposal that were not included in the already approved observations because they were assuming a much fainter object. So the lesson there is to prepare for contingency when it comes to science. So because you never know what you're gonna get.
Bryce, might you share how you got this time on Gemini and like the various pathways through which you were able to get time on Gemini, and also Keck when you did the first session there?
Yes. So I am only able to do these observations because some very nice people were willing to let me use their awesome telescope. Thank you, individuals at Gemini. Y'all are awesome.
Well, I want to say, Bryce, that I mean, you put in a very I mean, we didn't just gift you the time. You put in a very nice proposal, a very scientifically compelling proposal, and so that proposal was analyzed by our team here, a group of scientists, staff scientists, and we said yes, that's worthy of telescope time in the manner in which Bryce and your team were proposing for it, and so that time was awarded to you merit-based. Based off of our assessment of your proposal.
Well, I think that's very nice of you to say. And I've had support in developing that science from people like Matthew and Laura May, my collaborators. And I mean, this is not the project of an individual person, a single individual person. It really does take a village. Let's say a lot of different people contributing their insights and grouping it to one thing. So Gemini was very nice to consider my proposal and grant me this time. And Keck has a similar mechanism in which you can apply for time, and you make an argument. When you apply for time on a telescope, you have to come up with a statement that says what you're going to be doing with the telescope and why you need it, and what goes into the evaluation of that is the sort of the scientific merit behind that. Like how likely are these results going to providing new and insightful information on the object of study. Matthew as well, through James Webb, there's a mechanism for which you have to apply for time, and these are all pretty competitive. The rate at which proposals are rejected to those which are accepted is well, let's say the acceptance rate is not particularly high, especially for these premier facilities, these 8-10 meter class telescopes. And
yeah, just to give a kind of scale for that, anywhere between let's say 2% of proposals and 20% of proposals, depending on the exact mode, are accepted. And so this particular proposal came through our director's discretionary process, where Bryce sent in a proposal effectively directly to our director. Then our chief scientist delegated to a group of scientists here to analyze the proposal and to decide whether it would be awarded time. That's a different modality than, for example, a typical proposal where you would give a proposal at the we have 2 semesters, and so you propose at a semester boundary, and then that proposal is sent to a group of external scientists who then award the time. So and then we have an intermediate process called fast turnaround, which Bryce is a master of, and I support a lot of Bryce's programs on fast turnaround, which is what's called a distributed peer review. So you basically, in a dual anonymous way, you review your competitors' proposals, and they review your proposal, and then those ranks are then put together, and every month we award time, and these are usually like short time scale kind of observations. So Bryce was just awarded a time through fast turnaround to do near infrared observations of 3i Atlas, and so we're just iterating on that now, and probably in the next couple of weeks those observations will be, well, with any luck, will be taken. And I just wanted to contextualize, so we just finished the last IFU frame, And so that's read out here. So you now have all of your IFU data, Bryce. So start reducing.
All right.
Production engine's ready.
Right now, Bryce, let's get on that.
And we're gonna pivot to imaging. So I think it's time to go. Aaron, is that right? You guys are moving to imaging now?
Yep, that's correct. We are just waiting for the guider to settle, for the telescope to settle, and we'll be starting imaging, our first imaging frame in just a minute.
Wonderful, yeah. So all of our optics right now are just settling into place. We want to make sure we get the clearest image possible. And we've moved to a different guider from what we were using before, I think, maybe?
Yes, yes.
And so...
So as we prepare to transition, I want to...
Oh, it's P2 still, okay, yeah.
I want to bring up a question in the chat because there has been an astronomer that's been very viral. Oh, okay. Oh, okay. I didn't see it pop up in the chat yet.
Thank you.
Okay.
But I will go to another question. What is the estimated lifespan of 3i Atlas, and how is that determined?
Matthew, do you want to take charge of this one?
Starting science.
So actually, you might be better to speak on this, Bryce, because I haven't quite read all of like Daryl's papers on the computation of the estimated lifespan. I just know that most of what goes into that is the, where it's coming from and the incoming velocity / eccentricity, right? Just constraining that is the main sort of source of where we're getting the age from. But yeah, Bryce, you probably...
Yeah, well, there's been numerous other authors who have commented on this. So there's one thing which I would say is like the dynamical lifetime. Oh, is this the is this the comet?
Yeah.
Wow. Yeah, we want to make sure we're not saturating here. Let's see. Oh, wow, look at that.
Nope. Our counts are good.
Awesome. Okay. Sorry for the technical difficulty. All right, so that's our green image. Yeah. And counts look good?
That's
Counts
awesome.
look good.
Maximum. Oh, yeah, we're fine.
No saturated pixels.
46, 20, 84, 20. Oh, so we're only at like 15% well depth, so we can go deeper if you want, Bryce.
I would say I think we should keep it at this. Let's keep the configuration uniform, and just plug through the sequence. If we have time left over, there's a little extra time, maybe we'll take a few deeper images. But I think this looks fabulous. This just looks fantastic.
Well, so we are about 10 minutes away from 12 degree. So we're good now. So 12 degree is when the sun is 12 degrees below the horizon. It starts to get a little bit brighter. Let's see. So yeah, maximum 50 through 29. So that's fine. We saturated 65,000 basically. So I would. I mean, it's your science, but I would go deeper. So I can set up.
Do you think we could do 10 seconds? I'm sorry. Would 10 seconds take us above the saturation?
Depends on which band, but probably not. So this is the I-band image, 283, I think. So
That's I.
That's I. Okay.
So yeah, we can do 10 seconds if it's not going to take us above the
10 seconds. So we just did 1 second on I. So we probably go 5 seconds on I. So I can make it a second sequence. We're already here, so the overhead time is very short. So if you want to go deeper into it, I'll make a second sequence. But yeah, I think we're good to go. And so if you want to just keep plugging through that sequence, I'll copy. I'll make a second sequence.
Thank you.
Awesome. Thank you so much.
Are we in the middle of one of the chips, or are we close to the...
Yeah, don't worry about Marco's thing, because I dither between... It's a random dither, and it's not exactly in the center. Marco is very... he worries, yeah.
Yeah, but you can see
he's good.
You're way You're fine. So you're not anywhere near the gaps.
Great.
Thank you, Laura May.
Wow. Yes. Yes. So the study that Matthew mentioned by Astor Taylor and Daryl Seligman estimates that 3I Atlas is likely approximately 3 to 11 billion years old. That's just mind-blowing.
Yeah. So there's been numerous other studies on this as well, on the relative ages. There's one by this group of Oxford, and that is looking at this. And it honestly, the age really depends on where you assume the comet comes from in the galaxy. There's different structures in the galaxies that have different relative ages. Yeah, there's this one, but there's different ways of looking at it, addressing that question. Different groups have done their best to. There's Chris Linto's group at University of Oxford, which interprets something around 5 billion years. So that's kind of the dynamical age. You also have the structural age. How long does a object survive in interstellar space, being bombarded by dust and interstellar medium? And that is billions of years. So it's the age at which it would take for the comet to disintegrate from dust bombardment is very long. That process is very, very slow. And there's also something called the disk crossing time. So the relative amount of time that it takes for a object in the galaxy to go around the galaxy before encountering another object, before colliding with another object, and that's also billions of years, well larger than the age of these objects. And these dynamical ages are heavily based on how puffed up the galactic orbits of these objects are. So 1I Oumuamua has let's say the smallest vertical distance in the galaxy, whereas 3I Atlas has the largest vertical distance in the galaxy. And so the relative ages between the interstellar objects is scales with that distance. So 1I Oumuamua is the youngest age. It's projected to be hundreds of million to billion year range, where 3I Atlas is in like order of unity 5 billion years age, and 2I Borisov is kind of in the middle. But these are kind of statistical inferences, and our understanding of the true distribution of the ages of things in the galaxy is actually quite unknown. So there's kind of a unknown amount of uncertainty. We know there's uncertainty, but we don't know exactly how much uncertainty there is with the understanding of these ages. So I would take these dynamical ages with a large grain of salt. And the question keeps on coming up about Avi Loeb, and I think just gonna really briefly say this, kind of nip this in the bud. But Avi is a very well accomplished scientist who's done a lot of groundbreaking work in studying the early history of the universe, and he has a very broad and immense knowledge of astrophysics. As a theorist, probably one of the most profound.
Stands up by 133.
Yes, but my interpretation of the data and of the properties of these interstellar objects is that they all look they're all very comet-like. So, like as I mentioned, 3I Atlas has a greenish color. When you combine the images, the false color images, you have a green color. And many comets in our solar system, which we know originate from the solar system based on the orbital explanation that Matthew and I gave, we know that originate from our star system, also have a green color and exhibit a lot of the same properties. So I would say, kind of at a first order, there's sort of a refutation of this viral stuff, is that a lot of comets from our star system have this green color, exhibit properties of 3I Atlas. So are all comets alien spaceships, or all things that look like 3I Atlas comets? It seems to me that Occam's razor, the easiest explanation, the simplest explanation, is that it's a comet. But everyone is free to interpret the data and consider which things are facts and which ones are not. And if we all thought the same in the world, there wouldn't be any progress. There's many circumstances, there's many examples in science in the past where people have differing opinions, and sometimes the differing opinions for whoever is right or wrong doesn't matter so much. It's that if you have a difference of opinion, that leads to progress. A really famous example is Einstein. Einstein was right about a good many of things, but he was also wrong about a good many of things. But his insights in being wrong were so profound that it led to progress in science. So I mean, everyone can it's free to interpret here, but there's some amount of appreciation we have to express for people like Avi and raising public awareness for interstellar objects, for interstellar comets. There's a sort of a ripple effect that benefits from us as well. So I don't know if that satisfies your question. Maybe you were hoping me to say that these were alien spaceships or something. But
yeah, that was a brilliant response, Bryce.
Yeah.
Thank you so much. And I believe Raja may also add a little bit more to what you said there in the chat. But we have a few more questions here and an amazing image right here on the screen. And first question, I believe Brian already answered this. This is from Andres. How fast is 3i traveling? I think you said 300,000.
300,000 kilometers per hour. Yeah.
Per
that's
hour.
what I understand.
Yes. And then
my solar system dabbling.
Yes.
Okay. I'll just bring it back to the observations here. So we're going through a sequence right now. We're taking images in different colors. So you'll see the brightness of the comet change, and that's actually because we're looking in different colors. And we were a little bit conservative on the exposure time because we didn't want to saturate. We didn't want to basically blow out the camera. And as Aaron mentioned, nautical twilight's about 5 minutes, so the sky is starting to get a little bit brighter. That's 12 degrees, 12 degrees twilight. We're just about at the end of the sequence. So we're going to take one more GRIZ, so green, red, a little bit redder of red, and much redder than red sequence. And then we're going to go a little bit deeper. So I've set up a sequence, Bryce, for your edification. It's 133. And that sequence, I've basically multiplied the exposure time by a factor of 4. So we're going to try to get at least 2 GRIZ sequences out of this. Let's see if we can push it. And we'll just kind of go until we're starting to saturate. So hopefully we'll kind of bring out the larger scale features of the comet with this little deeper image.
Oh,
so let's see what we can get. This is like we're almost at astrophotography level here.
This is like so exciting.
Yeah, Emily put that there. It is really exciting watching the data and the images come in. Absolutely, it really is.
We're fighting the sun here, though. Yeah. So this is,
well, Brian, did we get all 4 bands GRIZ?
Yeah. So this is the last of 4 sequences of GRIZ.
Wow.
Yeah, so that was our image that just came out. Yeah, so this is our shallower exposure time. So this is going to focus more on the nucleus.
Ooh. Brian, can you quickly explain nautical twilight?
Yeah, it's just when the sun is 12 degrees below the horizon. Yeah, sky travels 15 degrees per hour. That's not the sun. The sky travels 15 degrees per hour. As Rob mentioned, near the equator, sun moves pretty quick. As Aaron mentioned, sunrise is about 50 minutes, but you don't want to be taking astronomical observations at that time. We actually do take some calibration observations. Aaron might have to stay up till sunrise because our IFU flat observations, twilight flat observations, are basically taken around sunrise. So I think Aaron mentioned the plan after this is to take some imaging flat data that'll help reduce the data that we're taking now, Bryce. So this is just kind of standard. We point to a part of the sky, random part of the sky that's hopefully relatively devoid of sources, and just move the telescope around a little bit and get an estimate of the sky background. So you can see there's feature as Aaron stretches this out, you can see these like banding features vertically. You can see some vignetting on the side, so some dark areas. And so all of that we have to take out. These are all different amplifiers of different chips of the camera array. And so all of that terrestrial noise, electronic noise, optical noise, we have to take out in order to get to the true source. So we just finished up. Yeah, so we just finished up that sequence. Aaron's already moved on to our deeper sequence. Let's see. I think just about to read out. Yeah.
We are about to read out the first of the deep. And also note in this image that darker region at the top is due to uneven illumination from the brightening sky.
Mm-hmm. Yeah. Yeah.
So we're already seeing the effects of the sun.
We're already seeing effects.
Yeah.
Yeah.
So question here, will there are there any chances for clouds to start forming while this is happening?
No saturation, Brian.
Awesome.
I'll go ahead and continue.
Yeah, please do. Yeah. So we'll keep an eye on these. So this is experimental. So these next three, we got to really keep an eye out for saturation. What are you getting maximum 35,000? Okay, so we're about halfway to saturation here. So we're still staying within. Oh no. Okay, 12,000. So 13,000.
Okay.
So yeah, we're doing pretty good, at least on that G image. So yeah, clouds could be a problem, especially for what we call photometric standards. So we take images of stars of known brightness in different bands, and that helps Bryce and his team calibrate out. So you get counts, basically. You get counts on an image. You need to translate that into physical units that are actually meaningful. Normally we work in units of what's called flux density. So it's basically energy per unit area per unit wavelength, or power. And so that calibration needs to happen. If clouds come in, we basically have to take the photometric standard before clouds come in. Luckily, Aaron is way ahead of the game, so they already took observations earlier in the evening of photometric standards, so no problem. We don't have to rush. IFU twilight flat is actually just to illuminate, just basically the pattern of the IFU and to get the night sky background. The clouds actually don't change that much, so it's more or less okay. But each calibration is different, so yeah, we have to be very careful about what's different between the actual observations. We don't want to induce any bias, so what's different between the actual observations and the calibration observations. So in the case of a photometric, where we're trying to get the absolute calibration of the brightness, we need to be very careful that the observations themselves are not different in terms of cloud cover relative to the calibration observations. So the science target observations are not different. It looks like we're still doing good. So we're now on the last band, and we're not saturating. So I think we're golden.
Yes. And thank you, Emily. You shared a current view from the Mauna Kea webcams, and if you click on that, you can really see how the sky is starting to brighten there.
But really not that many clouds coming overhead. It is a really, really gorgeous night on Mauna Kea.
Yeah, I can switch over to that really quick.
Oh yeah. Oh, that's incredible.
Although I guess it's technically morning, not night anymore.
Yes, it is.
Guys, I just wanted to add something to what others have said. I've known Avi for over 30 years. We were postdocs together at the Institute for Advanced Study in Princeton. Yeah, like over 30 years. As other people have pointed out, he's done amazing work in astrophysics. At the same time, I take a less kind view to what's going on right now. I mean, this sensationalism leads to personal gain in terms of money, fame, profit, but it does a lot of damage to the field. You know, if Brian were to claim that instead of walking in through the glass doors of the Gemini helo-based facility into the observing room, he quantum tunneled through the walls, that would generate a lot of attention. There's a finite probability that you can do that, Brian. There's an higher probability.
I'm not going to take my chances right now.
Yeah, it's a higher probability that you'd be better off going through the front door. But, walking through the front door doesn't generate publicity. Claiming that you've quantum tunneled will generate a lot of publicity of the wrong kind, right? That would put your reputation at risk, would put your job at risk, would put, I would say the entire field of astrophysics on a slippery slope. And that's what I think is going on here.
I think and it's also great for us to be able to have sessions like this where anybody can join in and really look at this data. And I think we're really coming across of, if it walks like it ducks and it quacks like a duck, it's probably a duck. And this takes a spectra like a comet, looks like a comet. And so it's like a comet. And so I think it's really easy, and it helps break down some of these barriers that science is accessible to everyone by being able to do sessions like this.
Yeah, I agree. I'll just add to that, Emily, which, I feel like sunlight is the best disinfectant here. Comet like the best disinfectant. And actually, so Bryce received this time on the telescope as part of this director's discretionary process. But as part of this process, it's actually a public service because there's zero proprietary time associated, what we call proprietary time associated with the data. So the data are accessible on our archive right now. And so anybody that's interested can take these data, reduce the data, so make them in a scientifically viable form using the tools that we have here at Gemini Observatory. And they're actually relatively easy to use if you know Python, the language, and you basically just put you install some software and you put some command lines in, and out pops some science ready data, thanks to our friends in the science user support department. And you can analyze these data yourself. You can go through the process of actually getting science ready data and asking questions of the data yourself.
27?
Yeah.
So we've just taken our last observation of Triami for the night. So yeah, it's definitely time to move on. The session's coming to an end too. The sun is coming out here in Hawaii. Time for us to go back to bed or start our day. I don't know. Certainly for the night crew to start wrapping up. So Aaron and Denise are going to start taking calibrations at the end of the night. So that would be imaging flats and also a twilight flat for the IFU for Bryce and his team to be able to use in the data reduction process. So yeah, if there's any last questions or any last things that we want to point out, I will say that a couple of members of the Gemini team who are not present tonight will actually be taking these images here. So this Jen Miller and Matthew Rodriguez, who are also science operations specialists like Denise and Aaron. They will be taking these images here and making very pretty pictures like the one that you see behind Bryce.
Yes.
And will be used to contrast that. So that'll hopefully will be in the next couple of weeks that we'll be able to see a very realistic false color image of 3i Atlas. And then I do also want to, so sorry, please, Bryce.
Did y'all want to use those images in a press release? Because I can hold off on putting them on various scientific.
Oh no, feel free to do anything that you would like to do. We'll just we'll put it out at some point, and it's no problem. So yeah, no worries.
And I'll be sure to send it in a follow-up email to everyone who's in the session. I'll be sure to send you a direct link to those images.
Yeah, we'll put it on our public site for sure.
Yeah.
And I want to say this is not the end for 3i Atlas in general, but certainly not at Gemini as well. Bryce has plenty of observations coming up. There's other teams that are observing 3i Atlas from Gemini. and all the Mauna Kea observatories will continue to monitor 3i Atlas. The Rubin Observatory, which just came online in Chile, taking images of the entire sky, effectively the entire, well, what they can see from down there, every 3 nights. I would say, I don't know anything about the science, but I would say it's relatively likely that we might see 4i within the next 6 months to a year. So it could be, this story is not done. And so this is just the beginning. This is our first peek of this interstellar object as it's come back from behind the sun, but we still have plenty more science to do.
Yes, we do. And I can't wait. And I hope you all will join us for those 4i sessions with Shadow the Scientist.
Okay, to be clear, we do not have a 4i right now. We're making a prediction that we're reaching a technological point that we are discovering these things at a steady pace right now, but there has not been a 4i yet.
So I'll just go back to a question that was asked earlier about the Atlas network of telescopes, which the size of those telescopes is 0.5 meters in diameter. So just by contrast, the Rubin Observatory is over 8 meters in diameter. So it's basically a little bit larger than the Gemini telescope. So to Raja's point earlier, question earlier, and Bryce's response, this can get much deeper. And so there's a lot more fainter objects in the universe than there are bright objects in the universe. And so it allows us to peer down and see fainter objects, fainter comets that may be coming from elsewhere in our galaxy.
Absolutely. Incredible. Incredible. I would like to have, there's one more question, and I definitely want to make sure we get to it. It's from Kenna. Have there been any fun stories about studying 3i Atlas that obviously didn't make it into the papers or the press releases? Bryce, Laura May, Matthew.
Yeah. Laura May, would you like to handle this one?
I'm just trying to, sorry, there's building construction work going in front, and so it's very difficult for me to speak. You might have some funner anecdotes to share about it. I mean, I don't know, to me, it's just great that it's different from Oumuamua and Borisov. And that's been, I don't know that we have fun anecdotes of observation. For me, it was cool because I was actually in Chile, very close to the Atlas Observatory when it was discovered, and I remember Bryce messaged me about it, and everyone was very, very excited. So that was pretty fun.
Matthew, we have some pretty interesting anecdotes with the Palomar observations.
The very first images we got were we're using uncommissioned or an instrument that was still in commissioning on Palomar. It hasn't even fully been released yet, and we're using the guider camera of that instrument to get GRIZ photometry. So instead of a dedicated camera like what you're looking at right here on the screen, we're using just the camera that was being used to guide and acquire the target to get some of the very first images of it. That's how we got the first colors of it, actually. And then we, went ahead and acquired the spectra. But the first few weeks of observations were quite tough. It was still firmly in the galactic plane, and we're dodging stars and, taking observations right in between the little gaps as it was passing through a very dense field. So it's fun and challenging times. It's easier now, I think.
Yeah, we were, I was in France at the time, but we were remote observing from Keck using their infrared camera. And the density of stars in those images was so high. It was a bit like, finding the comet was a bit like playing Where's Waldo. Or they call it Where's Wally in the UK, where you have like this guy wearing a striped shirt standing in like a crowd of people, and you have to like find him in these little storybook pictures. And so it's like Where's Waldo Comet Edition, trying to find 3i Atlas in this crowded mass of stars.
Thank you.
And then even after you find it, then you have to calculate the precise windows where you don't get contaminated by stars, and that is also, I mean, you're trying to fit observations in these like 5-minute windows, again dodging stars. I remember it was also right around 4th of July here in the U.S., Independence Day in the U.S., And so I remember I'm supporting a lot of these programs for 3i Atlas, and I remember I was watching like the fireworks in Hilo here with my family, and I was just getting, I don't even have email on my phone. I was just getting like nonstop text messages about like random, things that I have to like go set up. So I was like, oh yeah, those are cool fireworks. I like ran home and then like started setting up randomly. And then I think simultaneously we were observing Gemini South and Gemini North, and I was contact scientist for both programs. So I was like in two different hemispheres, two different. It's just crazy. I don't know how you guys do it, because the galaxies that I look at, nice and steady, don't change for billions. It's all fine. For this kind of science, it's just everything super frenetic when it happens, but it's very exciting.
It is very exciting, so much fun, and it's incredible to experience it live and in real time with all of you. And I would like to say just a huge mahalo thank you to everyone on the Gemini science team, the Gemini staff, for hosting us and for supporting Shadow the Scientist, because it takes buy-in from everyone here to make these sessions happen. From the day crew, getting everything ready, the instruments, the making sure the observatory is healthy, to everyone who makes the decisions about the queue. And even though this was director's discretionary time, still this is all folded into their planning. And it takes so much, and we are grateful to them, because without this kind of collaborations and these amazing collaborators like the International Gemini Observatory of NORLab, we wouldn't be able to bring this to you. So thank you everyone for supporting us. I put a link to our follow-up survey in the chat. Some of you have already responded to me that you're going to do it for us. Thank you so much, because that feedback we provide to our funders, which is the Heising-Simons Foundation. It's very important for them to see how much of an impact Shadow the Scientist has on our participants. So thank you for that. And I will leave it with Brian and Emily, because the sun is coming up now, and I have water in here, but I'm craving some coffee.
So I just put the link in the chat for everybody. If you want to actually go in and see the data, that's our archive. All of the data are public for this particular program, and you can download the data, you can preview the data, so play around with it if you like. That's what it's there for. And yeah, mahalo to everybody for showing up. It's been wonderful. I love seeing things that aren't just little dots.
Yes, that's right.
This is beautiful, and I'm ready to get some coffee. Emily?
Oh man, yeah. Yes. I'm ready for breakfast. And thank you for joining us from Malaysia, where it's 12 a.m. So thank you for staying up late.
That's right.
And I also want to say thank you to Aaron and Denise for allowing us to shadow them this evening. It's not an easy job what they're doing, and it's even less easy when you have tons of people commenting on what you're doing and looking over your shoulder. So thank you very much for letting us do this.
That's right. Thank you, Aaron. Thank you, Denise. And Bryce, Laura May, Matthew, you are stellar. You are amazing. Thank you for allowing us to shadow your work and for sharing it with us so openly and freely here for this session. And we're going to go ahead and log out. I see some people who are asking about the recording. I am going to grab some breakfast and I'll do a quick edit so that we can have the edited recording for this session up on our YouTube channel by the afternoon. All right.
Oh, wow. Okay.
Yes.
I just want to say thank you for thank you for your support. Thank you, Denise, Aaron, and thank you, Jamika and Brian, and thank you, Raja, as well. And I want to say thank you, everyone here, for being a fantastic audience.
Yes, I second that. All right. We'll join you. Hopefully you'll join us again in an upcoming session of Shadow the Scientist. Take care and aloha.
Bye-bye.
Aloha.
Everybody.